In the last segment, we learned about some evidence for the particle-like nature of light. Now, we've already seen a lot of evidence for the wave-like nature of light. That's that waves diffract, and only waves can diffract. So we see that light acts like a particle and a wave. It turns out that particles, like electrons, neutrons, and protons, they act like waves too. The first person to propose this was Louis de Broglie, and he was a French physicist, and he proposed that the wavelength of a material particle was related to its momentum. And so he proposed this equation, lambda equals h divided by the momentum, which we can of course write as h over mv. And this is the de Broglie wavelength for a moving particle. And what's crazy is that this was published in 1924, and this was this man's PhD thesis, and we're still talking about it. So there you go. And it turns out to be a very successful idea. The first evidence for this came from diffraction patterns from shooting electrons through a tiny little hole in some foil. And so notice here, we don't just get the little dot that we might expect behind the hole. Instead, we see a diffraction pattern. These rings, which are characteristic of the diffraction patterns, just like we learned about a few chapters ago for light. We see the exact same pattern for light, for electrons. Heck, we even see it for protons, and it's a little bit harder to do the experiment, but you can do it with neutrons as well. So we see diffraction patterns from material particles passing through small openings. Well, what diffracts? You know what? Waves diffract. Particles do not diffract. They just don't. So this is evidence to support de Broglie's theory that material particles also have a wavelength. And we find, as we delve in a little bit deeper, that matter exhibits all of the properties we associate with waves. All of them. So here we see a double-slit diffraction pattern from electrons. It looks just exactly like the one we saw for photons. These electrons are just straight up behaving like waves. And much like with the photoelectric effect, that here we are 100 years later, and no one has come up with a way to explain how the photoelectric effect works by using a wave-like model of light. In the same way, here we are 100 years later, and nobody can come up with a theory that explains how a particle can diffract. They just don't. Waves diffract. Particles don't. And so we just have to accept that these electrons are behaving exactly like waves. And what's really crazy here is that we can do this experiment one electron at a time, and guess what? You get the diffraction pattern. And so again, we have to accept, oh, that electron went through both slits at once. One electron is interfering with itself. It's got to be a wave, right? A particle can't go through both slits at once. And so this idea you have of an electron is like a little ping pong ball winging around the nucleus that's like a little bit bigger tennis ball maybe or something, right? No, it just doesn't work. Like this electron, it's not a little ping pong ball. It's a wave. But let's be clear. What do I mean by a wave? Right? Think about a water wave. Is the water the wave? No. The water is not the wave. The wave is the energy. It's the disturbance in the water. And so let's be clear. When I'm talking about a matter wave, I'm not talking about a whole bunch of electrons all carrying the wave. No, I'm talking about a single electron is just not even just, it's not a particle. It's a wave. It's a disturbance. Ooh, that's weird. Let's crank some numbers out. What is the de Broglie wavelength of an electron with a kinetic energy of 1 electron volt? Well, h over mv. Ooh, they gave us the kinetic energy, didn't they? I could just solve for the velocity and then plug the velocity in here and get my wavelength. I'm going to do a little bit of algebra instead. Then we're going to do k equals 1/2 mv squared. Bring my 2 over and multiply both sides by m. Gives me 2mk equals mv. And notice I've got 2 m's and 2 v's, so they're both squared. And so then this means that the square root of 2mk equals mv. I can throw that into here, and I have h over the square root of 2mk. And so now I can plug in some numbers. Let's go ahead down here and plug in numbers. H, well, I'm going to go ahead and use H in joule seconds. The mass of an electron, 9.11 times 10 to the negative 31 kilograms. And K, which notice they gave us 1 eV. Recall that 1 eV is 1.6 times 10 to the negative 19th joules. And so I run my calculator, and I get 1.2 times 10 to the negative 9 meters. So 1.2 nanometers. How does that compare to visible wavelengths? It's much shorter, right? Visible wavelengths are something like 400 to 700, 750 nanometers. So we're talking about more than 100 times smaller wavelength than visible light. We'll revisit that in just a second. How does that compare to the de Broglie wavelength of a 4 kilogram watermelon moving at 5 meters per second? Well, let's just see. So here we have, again, lambda, h over mv. We don't need to do anything fancy here. So this is just 6.6 times 10 to the negative 34 joules second. The mass of my watermelon is 4 kilograms. The velocity is 5 meters per second. And you can see here that we're going to get a real small number out. And indeed we do. When I run my calculator, I get 3.3 times 10 to the negative 35 meters for the wavelength. So, that's small. What does it compare to? Let's see, an atom's about 10 to the negative 10th meters. So this is a lot smaller than that. And nucleus is something like 10 to the negative 15th meters. So this is like 20 orders of magnitude smaller than an atomic nucleus. Do you think you're going to notice the wave-like nature of a watermelon moving at 5 meters per second? I don't think you're going to, right? So this is why we don't observe this in our everyday lives. Does a watermelon have a wave-like nature? I guess. Not really, right? Not really. Because the wavelength is so small that a watermelon is just totally a particle, right? There's no wave-particle duality if we're talking about a watermelon. Which is why your common sense is just not equipped to deal with this. Again, we have to accept where cold logic takes us and not what we feel like maybe is right. Our common sense and logic are going to go in two different directions here. So this has some practical applications, which if you're in a biological science, you may end up using this in your work. We've learned that the wave-like nature of light, it limits the ultimate resolution of an optical instrument. Right? We've learned that two objects can only be resolved in a microscope or a telescope, and resolved means able to distinguish from each other if their diffraction patterns don't overlap too much. Right? And so we've learned that larger wavelengths cause larger diffraction patterns. And so the resolution of optical instruments is limited by the wave-like nature of light. But recall that we got a number that was much smaller for the wavelength of an electron than visible light. And so it turns out we can use the wave-like nature of an electron to image things, and that's exactly what we do. So we've seen this picture actually once before, And here we see it again, but now we've talked a little bit more about the electron microscope. In the optical microscope, the wavelengths are hundreds of times greater than with the electron microscope. Therefore, the resolution is much, much lower. These are all fuzzy, and some of these you cannot tell whether there is 1, 2, or 3 little bacteria. But here, with the electron microscope and its incredibly small wavelength, we can see these bacteria quite well. Again, this is real stuff. Like, electrons really are waves. They really are. This is not just some intellectual game. It's like, as far as we know, this is actually how this world we live in works.